Imagine this. You're falling, not through air, not through water, through the fabric of space-time itself. In exactly 60 seconds, you'll cross a boundary from which nothing can return. Not light, not matter, not information, not even time itself. This isn't science fiction. This is what physics tells us would actually happen if you fell into a black hole. And the journey is far stranger, far more terrifying, and far more beautiful than anything Hollywood has ever shown you. In the next hour, we're going to take that journey together. We'll count down your final 60 seconds, moment by moment. But to understand what happens to you, we first need to understand what a black hole really is. We need to journey through the history of their discovery, the physics that governs them, and because what happens when you fall into a black hole doesn't just challenge your body, it challenges reality itself. The monsters hiding in space-time. Chapter 1. The Impossible Prediction. 1783, Cambridge, England. A geologist named John Michell writes a letter that will take humanity 200 years to fully understand. He asks a simple question. What if a star was so massive that not even light could escape its gravity? Using Newton's laws, Michell calculates that if you compressed enough mass into a small enough space, the escape velocity, the speed needed to break free, would exceed the speed of light. He calls these hypothetical objects dark stars. The scientific community largely ignores him. 1915, Berlin, Germany. Albert Einstein publishes his general theory of relativity, fundamentally rewriting our understanding of gravity. Gravity isn't a force pulling objects together. It's the curvature of space-time itself. Mass tells space-time how to curve, and curved space-time tells matter how to move. Within months, a German physicist named Karl Schwarzschild is serving on the Russian front during World War I. Between artillery barrages, he solves Einstein's equations for a perfect, non-rotating sphere of mass. The solution contains something disturbing, a radius at which space-time curves so severely that nothing can escape. The Schwarzschild radius, the event horizon, the point of no return. Einstein himself doesn't believe these singularities can exist in nature. He spends years trying to prove them impossible. He was wrong. Chapter 2. From Theory to Reality. The 1960s. Astronomers discover quasars, impossibly bright objects at the edge of the observable universe, pumping out more energy than entire galaxies from a region smaller than our solar system. No known physics can explain them. Then, breakthrough. John Wheeler, the physicist who actually coins the term black hole in 1967, proposes that quasars are powered by matter falling into supermassive black holes. The friction generates temperatures of millions of degrees, causing the matter to glow brighter than 1 trillion suns before vanishing forever. The 1970s. Astronomers find Cygnus X1, a powerful X-ray source in our galaxy. Careful observations reveal an invisible companion star, pulling matter from a blue supergiant. The invisible object is too massive to be a neutron star. It must be a black hole. Stephen Hawking famously bets against it being a black hole, a bet he'll later concede he lost. April 10th, 2019. The world sees the impossible, an actual photograph of a black hole. Not an artist's rendering, not a simulation, a real image of the supermassive black hole at the center of galaxy M87, assembled from 8 radio telescopes across Earth. The orange ring of superheated matter, the dark shadow at the center, the event horizon. 55 million light-years away. And there it is, proof that Einstein's most disturbing prediction was real. Chapter 3: The Taxonomy of Monsters. Black holes come in different sizes, each with their own personality, their own way of warping reality. Stellar mass black holes form when massive stars, at least 20 times the mass of our Sun, exhaust their nuclear fuel and collapse. The core implodes in less than a second, and if enough mass remains, not even neutron degeneracy pressure can stop the collapse. It becomes a black hole, typically 5 to 50 solar masses. There are an estimated 100 million of these scattered throughout our Milky Way galaxy alone. Supermassive black holes lurk at the centers of most galaxies, including our own. They range from millions to billions of solar masses. The one at the center of our Milky Way, Sagittarius A star, weighs about 4 million suns. The one in M87, 6.5 billion solar masses. We still don't fully understand how they grew so large. Intermediate mass black holes exist in a mysterious middle ground, roughly 100 to 100,000 solar masses. We've only recently started discovering them, and their origins remain hotly debated. And theoretically, primordial black holes, tiny black holes that might have formed in the extreme conditions right after the Big Bang. Some could be smaller than atoms, but weigh as much as Mount Everest. If they exist, they might even be the mysterious dark matter holding galaxies together. But for our journey today, we're choosing a supermassive black hole. Because with a stellar mass black hole, you wouldn't survive to reach the event horizon. The tidal forces, the difference in gravity between your head and feet, would rip you apart millions of kilometers away. A supermassive black hole offers something different. The chance to cross the event horizon while still conscious, still intact. At least for a little while. So let's begin your journey. Act 2. The Approach when time breaks down. Chapter 4. Choosing your fate. Your mission begins 10,000 kilometers from the event horizon. You're a volunteer, part of humanity's boldest experiment. Your spacecraft hovers at a safe distance while you prepare for your descent in a specialized probe designed to transmit data for as long as physically possible. Your destination, Gargantua Prime, a supermassive black hole 100 million solar masses, roughly 600 million kilometers in diameter. That's about 4 times the distance from Earth to the Sun. At this size, the tidal forces at the event horizon are survivable. You'll have precious seconds, maybe even minutes, before spaghettification tears you apart. The mission is simple. Fall in, observe, transmit everything. Become the first human to witness what lies beyond the cosmic censorship of the event horizon. You say goodbye to your crew. They know they'll never see you again. Not really. From their perspective, you're about to become a ghost, frozen in time at the edge of infinity. You detach from the spacecraft and begin your descent. Chapter 5. The Relativity of Reality 60 seconds from the event horizon. Here's where things get strange. Not horror movie strange, mathematically, provably strange. Einstein's relativity doesn't just predict this, it demands it. As you fall deeper into the gravitational well, time begins to dilate, not from your perspective. Your clock ticks normally, your heart beats normally. But relative to your crew, you're slowing down. From your perspective, you check your instruments, falling at 5,000 kilometers per second now, accelerating steadily. Everything feels normal. Time passes second by second, just as it always has. From your crew's perspective, They're watching you through their most powerful telescopes. Your descent is slowing. Your movements become sluggish, like video played at half speed. The radio signals from your probe are arriving farther and farther apart, stretched out by gravitational time dilation. 50 seconds from the event horizon, the light from your probe begins to redshift, the wavelength stretching like taffy. The bright white light of your probe's beacon shifts to red, then deep crimson, then infrared. Your crew needs special cameras now to even see you. But you see the opposite. When you look back at your spacecraft, the light is blue shifted, compressed by your motion into the gravitational well. Your crew appears to be moving in fast forward. You watch days pass in seconds, the stars wheeling overhead in accelerated motion. Dr. Sarah Chen, theoretical physicist, MIT. The paradox of the event horizon is that both perspectives are absolutely true. The falling observer crosses in finite proper time, their own experienced time. But from outside, it takes literally forever. Both are correct. This isn't a contradiction, it's relativity showing us that time itself is not universal. 40 seconds from the event horizon. Your crew is experiencing something profound and heartbreaking. They're watching you approach the event horizon in extreme slow motion. At this distance, time dilation is so severe that for every second you experience, hours pass for them. Your last transmitted words stretch out over minutes. Your movements become glacial. The computational systems on your spacecraft predict that from their reference frame, they'll watch you fade at the event horizon for centuries, millennia, perhaps until the black hole itself evaporates via Hawking radiation trillions of years from now. But you're about to do something they'll never witness. Crossover. Chapter 6, The Light of a Dying Universe, 30 seconds from the event horizon. You look up, or back, or out. Directions are becoming meaningless. The universe behind you is doing something spectacular. All the light from the cosmos is being gravitationally lensed, bent around the black hole into a shrinking circle. It's like looking up from the bottom of an impossibly deep well, but the walls of the well are made of curved space-time itself. In that circle, you see everything, the entire visible universe compressed into a glowing disk. And because of the extreme gravitational blue shift, you're seeing the universe's future play out in fast forward. 20 seconds from the event horizon. The stars are aging before your eyes. You watch stellar evolution on timescales of seconds instead of billions of years. Galaxies collide and merge. Stars explode. The cosmic microwave background, the afterglow of the Big Bang, shifts from microwave to visible light, making space itself glow with ancient fire. Some physicists speculate that in these final moments, a sufficiently long-lived observer could watch the universe die. The stars burning out one by one, the galaxies receding beyond the cosmic horizon as space expands. The final protons decaying after 10 to the 40 years. All of cosmic history from this point forward, compressed into your subjective experience. You are becoming unstuck in time itself. Chapter 7. Crossing the Threshold. 10 seconds from the event horizon. Your instruments are screaming warnings, but the readings make no sense. Space and time are becoming entangled, their roles blurring. The mathematics describe something impossible. At the event horizon, space and time literally switch places. Dr. James Morrison, astrophysicist, Caltech. Inside a black hole, the time coordinate becomes space-like, and the radial space coordinate becomes time-like. What this means is that falling toward the singularity isn't something you're doing in space. It's something that's happening to you in time. You can no more avoid hitting the singularity than you can avoid next Tuesday. 20 seconds from the event horizon. The stars are aging before your eyes. You watch stellar evolution on timescales of seconds instead of billions of years. Galaxies collide and merge. Stars explode. The cosmic microwave background, the afterglow of the Big Bang, shifts from microwave to visible light, making space itself glow with ancient fire. Some physicists speculate that in these final moments, a sufficiently long-lived observer could watch the universe die. The stars burning out one by one, the galaxies receding beyond the cosmic horizon as space expands. The final protons decaying after 10 to the 40 years. All of cosmic history from this point forward, compressed into your subjective experience. You are becoming unstuck in time itself. Chapter 7. Crossing the Threshold. 10 seconds from the event horizon. Your instruments are screaming warnings, but the readings make no sense. Space and time are becoming entangled, their roles blurring. The mathematics describe something impossible. At the event horizon, space and time literally switch places. Dr. James Morrison, astrophysicist, Caltech. Inside a black hole, the time coordinate becomes space-like, and the radial space coordinate becomes time-like. What this means is that falling toward the singularity isn't something you're doing in space. It's something that's happening to you in time. You can no more avoid hitting the singularity than you can avoid next Tuesday. 5 seconds from the event horizon, and then nothing. No wall, no barrier, no sensation whatsoever. You cross the event horizon as easily as crossing an imaginary line on the ground. From your point of view, there's no moment of crossing. One instant you're approaching, and the next you've crossed. The universe didn't announce it. Reality didn't shatter. There was simply a point in space that once passed made return impossible. You are now inside a black hole. And ahead of you, the singularity awaits. Act 3. Beyond the Horizon, where physics breaks. Chapter 8. The one-way universe you're inside. Take a moment to understand what that means. Every direction you can point, every path you can possibly take, every trajectory physics allows, all of them lead to the singularity. Up, down, left, right. These are just names for different directions of falling inward. In normal space, your light cone, the paths light can take from your position, points forward in time but extends in all spatial directions. Inside the event horizon, your light cone tips over completely. The future direction in time is inward toward the singularity. The past direction is outward toward the event horizon you crossed. You cannot go back, not because the gravity is too strong to escape, though it is, but because going back would mean moving backward in time. Dr. Lisa Martinez, quantum gravity researcher, Princeton. People often ask, what if you had a rocket powerful enough? What if you had infinite fuel? The answer is, it doesn't matter. You cannot escape a black hole for the same reason you cannot travel to yesterday. The singularity is not somewhere you're moving toward in space. It's somewhere you're moving toward in time. It's in your future, as inevitable as tomorrow. 40 seconds remaining. You perform an experiment. You shine a flashlight upward toward the event horizon you crossed. The light doesn't travel up. It curves, bends, and falls inward with you. Even light, The fastest thing in the universe cannot escape. You fire your thrusters at full power, accelerating upward with everything your probe has. It doesn't matter. You might slow your descent slightly, but the singularity is still in your future. You're like a salmon swimming upstream in a river flowing faster than it can swim. Chapter 9. The Cosmic Illusion. 35 seconds remaining. Above you, and that word is increasingly meaningless, the circle containing the entire outside universe continues to shrink and brighten. The gravitational blue shift is becoming extreme. The cosmic microwave background, usually at 2.7 Kelvin, has blue shifted into visible light, then ultraviolet, then X-rays. If you weren't shielded, the radiation would be lethal. You're being bathed in the compressed light of a trillion stars, all focused by gravity into that shrinking portal. 30 seconds remaining. Some theoretical physicists, Kip Thorne among them, have calculated what you might see in these moments. The answer is both beautiful and terrifying. You might see the entire future history of the universe play out in reverse. Not because time is actually flowing backward for you, it's not, but because the light reaching you is following paths through severely curved space-time. Light emitted by stars billions of years from now in the outside universe can reach you now, following geodesics that thread through the warped space-time around the black hole. You might see stars that haven't been born yet, civilizations that rise and fall in the distant future, the end of the universe itself. But you don't have time to ponder this. Chapter 10. The Firewall Paradox. 25 seconds remaining. Here's where things get controversial. For decades, physicists believed you would feel nothing unusual crossing the event horizon of a supermassive black hole. General relativity predicts a smooth, uneventful crossing. The principle of equivalence says free fall is indistinguishable from floating in empty space. But in 2012, a group of physicists led by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully proposed something radical: the AMPS firewall paradox. The argument goes like this. Hawking radiation, the quantum effect by which black holes slowly evaporate, creates entangled pairs of particles at the event horizon. One particle falls in, one escapes. But Hawking's calculation also shows that the radiation carries information about what fell into the black hole. Here's the paradox. If the outgoing Hawking radiation is entangled with the black hole's interior to preserve information, and the radiation is also entangled with its partner particle that fell in, as quantum mechanics requires, that's two entanglements. But quantum mechanics forbids a particle from being maximally entangled with two different systems. The proposed solution? The infalling particle's entanglement must be broken violently. The result, a firewall at the event horizon, a wall of incredibly high-energy particles that would incinerate anything trying to cross. This contradicts general relativity, which says crossing should be smooth. The firewall paradox has divided the community. Maybe quantum mechanics needs modification. Perhaps general relativity breaks down earlier than we thought. Or information is destroyed, and Hawking was right all along. We might need quantum gravity to resolve this. 20 seconds remaining. As you cross the horizon, you either feel nothing, or you're instantly vaporized by quantum fire. Our physics cannot tell us which. Both options seem impossible, yet one must be true. You feel nothing unusual. Either the firewall doesn't exist, or your neurons were destroyed too quickly to register it. Either way, you're past the point of knowing. Chapter 11, Spaghettification, 15 seconds remaining. Now the tidal forces begin their inevitable work. Tidal forces are simply the difference in gravitational pull across an object. The side closer to the mass feels stronger gravity than the far side. On Earth, this creates ocean tides. Near a black hole, it creates something far more violent. Your feet are closer to the singularity than your head. The difference in gravitational acceleration between them is growing exponentially as you fall deeper. 12 seconds remaining. At first it's subtle, a gentle stretching sensation, like someone gently pulling on your ankles. Your spine elongates slightly. Your vertebrae separate by millimeters. It's uncomfortable, but not painful. 10 seconds remaining. The sensation intensifies. Your body is lengthening, your bones creaking under the differential stress. At the same time, you're being compressed horizontally. The tidal forces don't just stretch you along the radial direction, they squeeze you from the sides. Your ribs press inward, your internal organs begin to deform. Blood flow becomes irregular as vessels stretch and compress. 8 seconds remaining. Pain erupts along every nerve. Your spine is elongating centimeter by centimeter. The muscles in your legs scream as they're pulled beyond their limits. Your skin stretches, blood vessels rupture. But the worst is the compression. Your chest cavity is narrowing, your lungs can't fully expand, your heart struggles to pump as it's squeezed from the sides. 6 seconds remaining. Your body is now visibly distorted. If anyone could see you, you'd look impossibly tall and thin, like a reflection in a funhouse mirror. But there is no one to see. The only light here is what you brought with you, and even that is being pulled inexorably inward. 4 seconds remaining. The tidal forces exceed your structural integrity. Your bones begin to fracture, your soft tissues tear, but you're falling so fast now, experiencing such extreme gravitational time dilation relative to your own body parts that the signals don't have time to propagate normally. The neurons in your feet exist in a slightly different time frame than the neurons in your brain. Can consciousness even persist when different parts of your mind experience time at different rates? 2 seconds remaining. You're no longer recognizable as human. The molecular bonds holding your body together fail. Cells rupture. DNA strands snap. You're becoming a stream of organic molecules, all elongating into a thin strand falling toward the singularity. But even as your body disintegrates, your atoms remain. They fall onward, toward the final moment. 1 second remaining. Ahead, the singularity looms, not as a place, but as an end to time itself. Act 4, the singularity, where equations die. Chapter 12, the final mystery. 0.5 seconds remaining. What is a singularity? Ask 10 physicists, get 15 answers. The classical picture, a point of infinite density where all the mass of the black hole is concentrated. Infinite curvature, infinite gravity, division by zero. The equations explode into meaninglessness. The quantum picture. Maybe there is no singularity. Maybe quantum effects, the uncertainty principle, quantum foam, space-time fluctuations, prevent the collapse from reaching a true point. Maybe the singularity is actually a region of extreme but finite density, just smaller than the Planck length. The Penrose diagram picture. For a rotating black hole, and all real black holes rotate, the singularity isn't a point, but a ring. The Kerr solution to Einstein's equations shows a ring-like singularity with bizarre properties. Pass through it, and the equations suggest you'd emerge into another universe, or a negative mass region of space-time, whatever that means. The information paradox picture. Perhaps the singularity is where information is destroyed, violating quantum mechanics. Or perhaps information is preserved in subtle correlations in Hawking radiation. Or perhaps it's encoded holographically on the event horizon. The loop quantum gravity picture. Space-time is not continuous, but made of discrete loops at the Planck scale. The singularity is replaced by a bounce, and the collapsing matter might emerge into another universe in a white hole explosion. We simply don't know. General relativity predicts a singularity, but we know general relativity must break down at quantum scales. We need a theory of quantum gravity, string theory, loop quantum gravity, something, to tell us what really happens here. 0.1 seconds remaining. Chapter 13, The Final Moment. What remains of you, a stream of atoms stretched into a one-dimensional thread, approaches the singularity. Time is not slowing down from your reference frame, it's ending. The curvature of space-time approaches infinity. The tidal forces approach infinity. The density approaches infinity. General relativity says, ρ approaches infinity, r approaches infinity, t approaches finite value. Density infinite, curvature infinite. Time ends at a finite value on your clock. 0 seconds. Silence. Chapter 14, The Holographic Tombstone. What happened to you? Where did you go? From the outside universe's perspective, you never crossed the horizon. Your image remains forever, frozen in time, slowly fading as the wavelength of light from you stretches to infinity. But there's another perspective, one of the most revolutionary ideas in modern physics, the holographic principle. In the 1990s, physicists Leonard Susskind and Gerard 't Hooft proposed something radical. Maybe the information about everything that falls into a black hole isn't lost. Maybe it's encoded on the surface of the event horizon like a hologram. From this view, you never really fell in. The three-dimensional you was scrambled and encoded as quantum information on the two-dimensional surface of the event horizon. There are two equally valid descriptions: the interior view where you're destroyed at the singularity, and the exterior view where you're smeared across the horizon. Which is true? Possibly both, or neither, or the question itself is wrong. Your atoms, your information, your pattern, everything that made you you, might persist in the quantum state of the event horizon until the black hole evaporates via Hawking radiation over 10 to the 67th power years or more. You're not destroyed, you're transformed. You've become part of the black hole itself. Epilogue. Living with the mystery. The unanswered questions back on Earth, in the everyday world of coffee and clouds and conversation, black holes seem impossibly distant. Abstractions. Mathematical curiosities. But they're real. There's one at the center of our galaxy right now, 26,000 light-years away, containing 4 million suns worth of mass in a region smaller than Mercury's orbit. Stars orbit it at 5,000 kilometers per second. We've watched them for decades, mapped their orbits, seen them whip around the invisible monster at the center. But maybe there's something profound in not knowing. The medieval world had all the answers. The Earth was the center, the heavens were perfect spheres. Everything had its place in the great chain of being. They were certain, and they were wrong. We've learned to embrace uncertainty, to say we don't know, and then work to find out. Black holes represent the frontier of that search. They're signposts pointing toward new physics, new understanding, new ways of comprehending reality itself. What happens at the singularity? What replaces Einstein's equations when they break? Is information truly lost? Do black holes give birth to new universes? Are we living in a universe that was born from a black hole in another universe? We don't know, but we're working on it, and that, the eternal human quest to understand, might be the most beautiful thing of all. This orange ring represents 100 years of mathematics, physics, and human ingenuity. It represents the genius of Einstein, Schwarzschild, Hawking, Penrose, and thousands of others. It represents our species looking at the universe and asking why. And the universe, through the mathematics of curved space-time and quantum fields, is beginning to answer. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Carl Sagan.